I agree. She's like, oh, it was great. And oh, it's right. That's what I was doing.
Okay, so we were looking at this example where it's not just exponential growth, but we are adding an additional complication where we're like, in this case, instead of just continuous compounding interest, we also are putting in a deposit or even a withdrawal is possible to model as well, which we'll do in a moment. And the way we did that was we took the original differential equation, which is dp over dt is equal to kp, which is in this blue box here. This is just saying that the amount of money, the rate of change of the amount of money in my account is proportional to how much money there is in the account at that moment. But then if we also said that this dp over dt is like dollars per year, is not just affected by this compounding interest term, but also by some fixed deposit or withdrawal. So if this was like 100, positive 100, then it's a deposit. But if it's minus 100, then it'll be withdrawal. Then you would have two terms on the right-hand side. You can write this in standard form by shoving all the unknown variable and its derivative. So P is like our X in this problem onto one side, and then everything else on the other side. But we're assuming that we're depositing some constant, known constant amount of B n times a year. And so this whole thing on the right-hand side is a constant, so it falls into the constant forcing case for method of undetermined coefficients. And so you could solve for, like, you plug in capital A and solve for that, and then you apply the initial conditions, and you get something more complicated looking like, that looks more complicated like this. And, like if we looked at each individual problem separately, so like the compounding interest by itself gives you this solution, which is like the exponential growth model that we saw before. And then if you look at the constant input, like if your constant deposits of 100 per year, the solution to this equation, if you're not including compounding interest, would just be 100t plus c. That makes sense because this is just modeling the amount of money in the account. And if you're just adding $100 every year and t is measured in years, then this is how it's going to change, where c is the initial condition. But if you have both of them happening simultaneously, it's not just simply taking this and adding 100t plus c to it. There's a much more complicated relationship between the two because they interact. The interest that you're accruing is actually interacting with how much money you're putting in, because as soon as you put money in, you're going to accrue interest on that. So they're not mutually exclusive from each other. They're actually talking with each other. And so you want to model this by writing the differential equation, which is based off of rate of change of the money, which has two terms to it, and then going through the method of undetermined coefficients to solve it, and you get something that looks more complicated than just simply adding these two solutions that are separate from each other. And so there's some assumptions, like you have to assume it's continuously compounding, and then also you're doing continuous deposits, because all of this whole model is a continuous model. It's not a discrete model. In reality, you might be depositing money not continuously, but in these discrete steps. And even though I have these vertical lines, they would be modeled as step functions, and step functions are discontinuous. So we're looking at continuous models. And we looked at these problems where the first one was just you're investing $10,000, accruing 12% annual interest, and then you're not doing anything else and just letting it sit there. Then your money is going to grow after 10 years. It'll be like over triple your initial amount, given that you're having a 12% annual interest compounded daily. So the other one was, say, suppose you make an investment of $1 a day. How much will your account have after 10 years? So that is not just continuous compounding interest. You're also making a deposit. So you're going to have to go back and look at, like, basically, I'll copy and paste this model right here. So you need to use this model where you have both these terms. So the first term is going to be your interest rate. K is 12%, so 0.12. times P, plus the NB is just saying how much you're contributing is $1, so B is 1, times how much you're doing it over the whole year is 365 because it's daily. And you would move the P term to the left-hand side, so you have this written in standard form. And so you'll get this equation. And you can solve for. So let's just do it then. So we'll just say that this is a constant right-hand side. So our particular solution, which is P, will equal some constant A. And you want to plug it in. If you plug it in, the dP over dt is 0, because that's just the derivative of a constant. And then it's minus 0.12 times A is equal to the 365. So you'll just have to divide both sides by -0. So therefore your A is 365. I'll do negative 365 divided by 0.12. And that's going to be your particular solution. Your homogeneous solution is, you can just read that off. So basically your general solution is going to be equal to your particular solution, which is what we just got. It's a constant particular solution. And then you're going to, so I'll make that purple. And then you're going to add to it the particular homogeneous solution, which is, reading off this is just going to be C e to the positive 0.12, because you're just taking the negative of it. And so this is how you build a general solution. This is your particular solution, or this is your homogeneous solution. So I'll do P sub H. And then this is your particular solution, which is P sub P. But you also well, you want to know how much there's gonna be in the account after 10 years. So you need to, build the full general model. Well, you want to build the model that's represented by this problem, which is got an initial condition. So basically we know that P of 0, the initial investment is $10,000. So you'd plug this into this as this is your general solution, but then you want to find the actual solution for this problem. You'd plug in this $10,000 into the P, 10,000, negative 365 over 0.12. What does this initial condition give us? It gives us a way to solve for this C. You got e to the 0.12 times initial condition says that t is equal to 0, so that's 0. So your C is like this e raised to 0 is just 1. So you're just gonna have a C that's equal to this $10,000 plus this term right here, which is the 365 over 0.12. So that's your C that goes into here. And you're basically have the full model. So you're just going to say that P of 10 is what we're ultimately interested in, is going to equal this 365 over 0.12 plus this giant thing. So I'll just copy and paste it. This is your C. That's all in parentheses. This is all your C. E times 0.12 times the 10, right? Because clearly you're interested in when this is equal to t is equal to 10. And of course, this is, just gonna be something you gotta do on your calculator. And you'll get get this. So it's a harder problem because you this first one was just if you had your money put in your account and you don't deposit anything, you just let it stay in your account and have interest compound. It's this very simple model here, and it just results in it tripling over tripling because 10,000 becomes 33,000. But if you put in $1 every day for 10 years, then you'll end up actually having more money in the end. So it's like you're just contributing $1 every year for 10 years. So it's going to be like $365 times 10. So it's like times 10 is $3,650. What's the difference between this 42? So 3,650, but then if you had this 40, let me just do this on my calculator, 258 minus 33201. I see. So the difference between this and this is like around $7,000. And but if you contributed $365 every year for 10 years, it's just adding a zero after this. So because of interest, your actual difference is more than your actual explicit amount of contributions you're making. And so that's the benefit of having compounding interest. We did all this work, but in reality, you could have just used this formula right here, because this formula right here already has everything solved in terms of how much you contribute, which is B, how many times you contribute is N. We basically solved this general problem where the K, N, and B were just left as variable. Well, they're not variables, they're just parameters in this equation that are just kept in general so that you can just plug in those parameters based on the problem at hand. So we could have just skipped doing all this work and just use this result that we got earlier and just said that for our problem, this model would have been, well, it would have been equal to, well, you don't have to write it because it's basically the same thing as the one on the top. So if you notice this right here is the same as this right here. The N is 365. The B is 1, so the top of 365. The K is 0.12 because that's the annual interest rate. The initial amount was 10,000. That's P naught. Again, NB, because it's 1 times 365, is just 365. The K is 0.12. E raised to the K was 0.12. And then the T, which we're just interested in computing it when its T is equal to 10. So this is just to confirm that our general model that we had earlier, that we derived earlier for general equation of this form, KP plus NB on the right-hand side, is consistent with this process we just did. We basically repeated the same process we did up here, but with actual numbers for N and B and K. But you could have, we already did it without actually specifying what those are. So the final form of this is correct for all cases. You just plug in your, N and B and K that's, reflective of the problem that you got at hand. And so you're welcome to just use this final result if you want to. If you want practice, then you can go through this process. But if you understand where it came from, this is the general solution for all these cases. So you could have just used that directly, which is probably what we'll do for part C. Suppose instead you withdrew $1 a day. How much money will you have after 10 years? So I'm just going to, again, just grab the final solution. Because you're doing a withdrawal, you know that it's not just interest. You're also having an effect due to the withdrawal that you're putting in. And you're in this case, you just plug in all the things that you know about this problem. So you will have P of T is equal to, so you're withdrawing $1 a day. So I'll just write all the parameters on the side here. So what do we have here? We're still doing per day. So your N is 365, but your B is now, what do you think? -1. That's the only thing that changes because K is still, so K is still this. And those are all and then P naught is still So that's it. That's the only change that you see. So you're just going to have the negative is still here. And then you'll have your n is 365, but you multiply this by -1. So that's the only change that you'll see. It's -1 here. And then you'll have divided by 0.12, so your k, plus your p naught is 10,000, plus your n is 365. Your b again is -1, so that's something else that was new. And then you're dividing this by your k is 0.12 multiplied by e to the 0.12 t. And you're interested in how much money you'll have after 10 years. So the only thing you're doing now is you're just plugging in this t is equal to 10. And if you got to type all this in your calculator, which is kind of annoying, but if you do, then you'll get that this is approximately 26144. You still end up having more than what you started with. That's because 12% annual interest rate is really, really high. So you put in $10,000, but you're still withdrawing $1 every day. You just think that you'd have less money after 10 years, but you actually have more than double what you started with, is because the amount of money that you are accruing or gaining due to interest is greater than the $1 that you're withdrawing per day. There's a U? Yeah, that's an N. Oh no, yeah, sorry, that's an N. It's just an N. So N is the amount of times you are withdrawing or depositing some amount. So that's going to be different now for part D, because it says how much can you withdraw each month if the account is to be depleted in exactly 10 years. So suppose you just want to use up all this money. I don't know, maybe you're expecting that you're going to die in 10 years, so might as well just spend it all. So you want to plan. You don't want it to all run out. You just want to run out exactly at 10 years. And you're just thinking, like, how much can I actually withdraw from this so that by after 10 years, it'll be all depleted. That's part D. So you're going to just say, again, you're doing a withdrawal. So it's really going to be, so I guess like for thoroughness, I'll just like write not just the solution, but I'll just write the differential equation. So up here, the differential equation was dp over dt is equal to the 0.12, which is the kp, plus the, it would have been plus the 365 times the -1. So this would have been the differential equation for part C. For this next one, the differential equation is going to be dp over dt is equal to, you still have the same interest rate, but you're interested in computing, like, so you're going to do plus, you're going to do monthly because you're just trying to withdraw each month. So n is 12. And then you're going to have that multiplied by b. And we're not sure what this b is. We want to find a b that will end up giving us that the p, which is the amount of money in the account, will end up just being 0 after 10 years. So this is the differential equation for this problem. But we already know that the solution is like of this form right here. So I'll just copy and paste this. And we just fill in all the relevant information. So in this case, the B is going to just stay, but you'd end up getting, so I'll just write it below. So for our problem, it's going to be negative n is 12 times, because it's monthly, so I'll just say n is 12 because it's monthly. Times the B. Of course, your interest rate is still 0.12, plus your initial amount is 10,000, plus your 12 is your n, b over 0.12, times e to the 0.12 t. So this is the model with b kept unknown for now. But what do we want? This equation is what we get from this. What do we want? And I'm, obviously I'm just using the result we had earlier that this is equal to the solution to this would be, this form, which you would be able to do by using the method of undetermined coefficients. Now the question at hand says, how much can you withdraw? So you want to find B such that the account is 0, so depleted in exactly 10 years. So you're going to plug in P. What would P have to be? 0. So you're going to say 0 is equal to all this stuff, but then T has to equal what? Like, is 10. And if you look at this equation, this is times 10. There's only one variable. E is not a variable. The only unknown is this capital B. And so there's just a bunch of algebra that you have to do, which I'll just post this algebra after, because I feel like it's going to be a pain to just watch me do the algebra. But you'll get that B is equal to negative $143.10. Is everybody okay if I just post the algebra to solve for B here? Because all you do is you move this to the left. Well, you actually will probably want to distribute this E to each of these. And then there's one term that doesn't have a B, so you can move that to the other side, and then you factor out the B. The B is already not in the power, so you can just divide through. And so you'll get this. And this is negative because if you're trying to force this thing to deplete, then it automatically puts the right sign on this B and says, well, if you want this P to be 0 in 10 years, the only way that's going to be possible to do is if you actually have a B that's negative. So if you actually withdrew, it would be really weird if you were contributing money and it was saying that, it's going to deplete after you contributed money. So this is saying, okay, you can, pull out $143.10 every month. And that will be how much you can do. So if you, this is like, let's say you had the $10,000, but you don't have interest. So I'll just say without interest. This is higher because you have interest involved. So if you had without interest, you'll have your $10,000, right? Which is the amount that you initially have in the account. And then 10 years. In 10 years, you'll just say divide it by 10. That's how much you can spend per year. Divide it by per month is 12. Is approximately $83.33 per month. So without interest, if you wanted to take your $10,000 and just spread it out over 10 years and how much you can withdraw per month, it's only $83.33. But if you have this annual interest rate of 12% and you're, withdrawing progressively every month at an equal amount every month, and you want it to deplete all that money, it's not going to be just 83. It's going to be, at least 50% or 70% higher than that, because you're also gaining from interest. So you're able to pull out more money than just dividing your original principal across 10 years. So that's it for exponential growth models. It's just the bacteria pop thing, and then also the there are many other applications that I could have used, but I decided to do finance stuff. Any questions about that? So we're going to now go backwards and think about like this idea of not exponential growth, but exponential decay. And a common application for that is radioactive atoms. So there's like some underlying physics that is basically says there's a fixed probability that your substance, which consists of radioactive atoms, will radioactively decay in some given time period. So there's some like unstable nucleus that breaks down and releases radiation energy. And there's a let's say the fixed probability that it will decay is like 50%. Let's just say it's 50%. So there's a 50% chance that in every time step, 1 second or 1 millisecond or whatever, you would end up decaying, breaking down. So not all the atoms will break down, because it's just a 50% chance. But, you know, in the large number of atoms that you have, you can assume that like half of them will, or approximately half of them would decay in a given time period, and some of them won't decay. So if you had 100 grams of radioactive substance, after one time step, it'll be 50 grams. After another time step, it'll be 25 grams. And then it'll be 12.5 grams. And then it'll be like 6.25 grams. And so it's just going to take whatever you have at that moment and half of them and half of them and half of them. So if you look at how much it's changing from here to here, you are decreasing by 50. From here to here, you're decreasing by 25. From here to here, you're decreasing by 12.5. And then from here to here, you're decreasing by. So the rate that you're decreasing is not constant. And it depends on how much you have at that moment. This is pretty similar to what we saw before, but kind of in the opposite direction. So before, we had that the rate of population growth was proportional to the population at that moment. So if you had like 4, then you're going to increase by 4, and then you have 8 now. In the next time step, you're going to increase by 8, and you're going to increase by 16. And so every single time step has a higher amount of delta P over delta T rate of change, but it's proportional to how much you have at that moment. And so this plot suggests that the rate of decay for a radioactive material is proportional to the number of decaying atoms present. So what's the differential equation describing the rate of radioactive describing the rate of radioactive decay? It's going to be like the dP over dt, which is the rate of the amount of radioactive substance, is proportional to the amount you have at the time. But this by itself would look like it's just growing. So what do you think I have to do in addition to just writing this? So I'll give you a hint here. The claim here is that at every single time step, this is like our dP over dt. Yeah, did you have an idea? Yes, exactly. So these red things are just trying to capture your rate of change at every single time step. And it's actually all of them are negative. You notice they're all negative, negative, negative. So your dP over dt is proportional to how much you have at that time, but it's negative. So I'll just put that negative. And so you have negative P. And proportional means that your dP over dt, so your rate of change of your amount of atoms, is if the plot is amount versus time, the rate of change of amount of time versus time is what feature of this graph? This slope, right? And if you look at the slope, when you have 100 grams, you have a very steep slope. So your dP over dt is quite steep. But if you have 25 grams, your slope is less steep, and then it becomes just less and less and less steep as time goes on. And so your dP over dt is negative the whole time, but how steep it is, how much of a negative it is depends on how much population you have at the time. So your 100, you're going to be a negative, but much steeper than if you had 25 grams, still negative, but less steep. And so this P, could be 100, then it's going to be negative 100 is your slope, where it's going to be negative 25 is your slope. And so that's just capturing the fact that, it's proportional to the number of decaying atoms present, which comes from this, physics of some fixed probability that it will decay in a given time period. So it's like you have how many atoms at the time, and if you have 50% decay probability, then the more atoms you have, the more of them are going to decay, and then there's going to be less, available atoms to decay in the next time step. And so that's why your dP over dt is decaying or is decreasing each time step. So this is your model that's proportional to the number of atoms present. And this is the differential equation representing the rate of radioactive decay. And the way we write it, okay, so maybe I should have put a box around the actual equation. So if you have something that's proportional, this symbol means proportional. If you want to write it as an equation, it becomes negative kp. You add a proportionality constant k. We're going to assume this k is positive because if we had a negative k, then it'll be multiplied with this negative sign, and it'll look like you have not radioactive, you'll have exponential growth. But this is your proportionality constant. But we know how to solve these equations because you could just shove this term to the other side. So you have dp over dt plus kp is equal to 0. This is a homogeneous equation. So your p of t will equal c e to the whatever is in front of this p is positive k, so it'll be negative k t. The only difference compared to the exponential growth model is there's this additional negative sign there. And you can show that, if you apply the initial conditions to this, so let's say you had an initial condition where p of 0 is equal to p naught. You could even look at this and say that means that this p is p naught whenever t is equal to 0, so c must be equal to p naught. So given this initial condition, so your general model will be p naught, e to the negative kt. And that's the general solution for this with some initial condition where you have the initial amount is equal to p sub 0. So let's do one problem. Suppose you have an initial mass of radioactive material that's 50 grams. It decreases to 10 grams after 3 days. What's the mass of radioactive material after 4 days? You're still going to use this model, but you're just going to plug in information to find different things. So we know that first of all, our P naught is equal to 50 grams because that's the initial mass. So you'll have P of T is equal to 50 times e to the negative kt. And then it decreases to 10 grams. So your P naught's given, but you still need to find your decay rate, which is K. And you're going to use the other piece of information they give us, which is this: after 3 days, you have 10 grams. What does that mean? That means that P of 3 is equal to 10. So let's plug that in. 10 for P, 50 e to the negative k times 3. You can divide both sides by 50, so you get 1 over 5 is equal to e to the negative 3k. You can take the ln of both sides. Okay, so just do that. ln of 1 over 5 is equal to negative 3k. And then you can just divide by negative 3. And so you'll get k is equal to ln of, well, I'll put a negative ln of 1 over 5 over 3. And I did say that k had to be positive, but it looks like there's a negative sign. It's okay because ln of 1 over 5 is negative. And so, I mean, you could even do this simplification. So this is the same as ln of 1 over. So there's this property log property where you can just pull this negative up as an exponent. So you'll get that is equal to negative 1 up here, divided by 3. And then, of course, 1 over 5 raised to the negative 1 is the same as ln of just 5 over 3. So if you want, this is just the same. These are both the same, but just simplified. This one's simplified. So that's your your decay rate. And you're just going to plug that into this k here. And what do we want? We want to know what's the mass of the radioactive material after 4 days. So what's the mass of the radioactive material after 4 days? So that's going to be the equivalent of finding P of 4. So your P of 4 is going to equal your 50 times e to the negative k. So this right here is going to be your k. And then you're just going to, so I'll just write it with this t here. So it's e ln of 5 over 3. But the t here, we want to be equal to 4. So really, it's going to be the same as 50 e to the negative 4 ln of 5 over 3, which you just put in your calculator and you'll get 5.85 grams. So you have 50 grams, and after 4 days, so initially you have 50 grams, but after 4 days, you're just gonna have only 5.85 grams because you're gonna have a lot of it decay. How long will it take for the amount of radioactive to be half? This is called a half-life. So this is similar to doubling time. You're just gonna say, this is our actual model. But what do we want for the time, if you want to find the time for this to become half, that means the P of T, which is the final amount, has to become half your initial amount. So I'll just write that right here. It says this is like saying you want this to be 2, or not 2, 1/2 P naught. So then you'll end up getting this. And your P naughts will cancel because you could just divide both sides by it. And you're left with half is equal to e to the negative kt. And then you just solve for the t. So you're trying to find the time that this happens to get ln of half is equal to negative kt. And then your t, so I'll just say t is equal to ln of half. So the negative, because you're having a negative here, okay. And then I guess you could also pull this negative up and this exponent. So then you'll end up getting that this is equal to ln of the 1/2 raised to the negative 1 over k, but 1/2 raised to negative 1 is the same as ln of, is the same as 2, so it's going to be ln of 2. So therefore your half-life is just ln of 2 over k. And you'll probably notice that this is the same, ln of 2 over k was actually the same as the doubling time expression. Doubling time here was also ln of 2 over k. And the reason is because the half life, and for the time something, and we have exponential growth, the time for it to actually double versus if you have exponential decay, the time for it to be half is just dependent on the rate k. The rate k just dictates how quickly, either in a growth situation it will become double, or in a decay situation will become half. And so they basically are the same amount of time it takes if the k, the rate constant k is the same. And so that's just an observation that you can make about both these two cases. And so that's actually, so rather that's relatively simple. The only thing was you just have a negative in front of this k, and all the other process is kind of the same, and you may have seen this before. So I'm just doing one example because then we can actually move on to another application, which is the thermal cooling. And this is more interesting, I think. So we'll just move on to it, unless people have any questions about the decay problems. Feel good about that. Okay, so this one's just trying to predict how an object is going to, the temperature of an object is going to change when you're putting it in some environment, assuming that the environment is not the same temperature as the object. So, you know, it might be hotter or colder. Your object is gonna actually not stay in that temperature. And the Newton laws of cooling says that the rate of change of the temperature of an object is proportional to the difference between the temperature of the object and the temperature of its surroundings. And they sometimes call that temperature of the surroundings the ambient temperature. This statement makes perfect sense because if you had coffee and it's hot and you just like have it sitting on this table, assuming that your coffee is probably like not boiling, but it's like hotter than the temperature of this room, you would assume that your coffee is going to cool down to the room temperature. But how fast it cools down to room temperature depends on how cold this room is. So if you took that same coffee and you put it in the fridge, then it's also going to cool down, but do you think it will cool down faster or slower? cool down faster than if you just had it sitting in this air-conditioned room. That's why this is saying that the rate of change of the temperature of the object is proportional to the difference between the temperature of the object and the temperature of the surroundings. So if you're in the fridge, then the temperature difference between the coffee and the fridge is very high, or I mean, it's higher. So that means that the rate of change of the temperature of the object will be, is gonna be faster. It's gonna be greater in the negative, obviously. So you got to get the sign correct, but essentially, it's going to cool down faster than if you ended up putting it in just room temperature. So what does this statement mean? This statement is saying that so let's just say let's label these things. So rate of change of the surface temperature of an object, we'll just say rate of change is like, we're just going to use D capital T over D little t, where capital T is the temperature. So I'll just write that. And so capital T as a function of time is the surface, I guess they technically surface temperature, but we'll just approximate that. We'll just say the temperature of the object is the same. And the temperature of its surroundings, the book likes to use this symbol, which is this big Q with a little 0, Q naught. So what's the differential equation describing Newton's law? Well, it's just saying that your change in temperature of the object, which is dt over dt, is proportional to the difference between the temperature of the object, which is the capital T, and its temperature of the surrounding, which is Q naught. So this proportional symbol is just saying that this is proportional, and then we'll make this an equation by multiplying by a proportionality constant. But let's just make sure that we are in agreement with this mathematical statement. Just for checking, let's just say, suppose the temperature of the object is the same as your surrounding temperature, then clearly this T minus Q naught would equal 0. And that'll mean that your dt over dt, so d capital T over d little t, is equal to, because T minus Q naught is equal to 0, I mean, I guess I could write the actual equation like this down here. It's going to equal K times T minus Q naught. You're just introducing a proportionality constant. So in this case, your d capital T over dt would equal what? If your T is equal to 0, then that means your T minus Q naught is, T is equal to Q naught. If the temperature of the object and the ambient temperature is the same, then T minus Q naught is equal to 0. So from this statement, your dt over dt would be 0. This is saying that if the object and your surrounding temperature are the same temperature, then the physics is saying, this equation is saying that the rate of change of your object temperature should be 0. So it's like saying if your coffee is already room temperature and you're just letting it sit in your room temperature room, the temperature of the coffee is not going to change. It'd be really weird if it started getting warmer or suddenly getting colder because it's already at room temperature. So that checks out. Okay. Now, what if you had a situation where your temperature of your object, which is your coffee, is hotter than your ambient temperature? Then your right-hand side has this T minus Q naught. This T minus Q naught would end up being greater than or less than 0. Greater than, because your T is bigger than your Q naught, which means that your dt over dt will be greater than or less than 0. Greater than, assuming that K is a positive proportionality constant. Does this make sense though? Because if your temperature of your coffee is hotter than your room temperature, it's saying that the temperature of your coffee is going to increase. Does that make sense though? Like if you have like warm coffee in the room, capital T is greater than Q naught is saying that you're actually hotter than your room temperature. So let's say your coffee is like 90 degrees, and then your room temperature is like 60 degrees. It's saying that you're actually going to get warmer. That doesn't make sense. So this is not quite the right form, but I can easily fix this by just saying that instead of T minus Q naught, why don't we say maybe it's really supposed to be this? It's Q naught minus T. I just wrote exactly what it said, temperature difference between the temperature of the object and the temperature of the surrounding, but it never said like, you know, what difference? Is it like the temperature? This is still the difference, but you're just taking the surrounding temperature minus this. And if you do that, if you had T is greater than Q naught, then your Q naught minus T will be less than 0. And then you have that this is this direction is actually decreasing. And so this also should be changed to Q naught. So this ends up being, well, this ends up being the correct differential equation. So the differential equation describing Newton's law is actually this. But it's good to check. It was good to check the signs are correct. And so it's really the difference between the temperature of the object and the surrounding, but that difference is written in this order. And then we'll be able to use this equation to solve a bunch of problems involving cooling and heating of objects. So we'll do that next time. I updated the class calendar, the Google Doc for the class calendar, to have our test not next week, but the week after, because I'd want all of these word problems that we're covering. So we have Newton's law of cooling. The next one's mixtures. And then I want those to be included on the first test because they're basically first order equations. And then after that, we'll cover second order equations. And it'd be nice to not have like any first order stuff lingering. And so I'd rather just like have this wrapped up, but it's too aggressive to have you have the test next week, even though we'll probably finish this material this week. I want like a week to have you guys digest. Have a good day.